Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in Chapter 3, part of this playlist, which I'm calling Characterizing Multivariate Data. So let's jump to today's topic, which is bivariate correlation. Now in statistics, correlation is any statistical relationship, whether it's causal or not, between two random variables or bivariate data. Now, however, most use it to mean the degree to which a pair of variables are linear related, which is what we'll use. So there's so many definitions of correlation. Now, the most common is probably Pearson's correlation, which is what we will use, which describes the linear relationship between two variables. Now, the population correlation, let y be a random vector of two variables. The correlation between y1 and y2 is a normalized covariance. Now, covariance was the previous video, and which is sensitive only to linear relationships between two variables. So here's the population correlation, which denoted by rho 1, 2. Now the 1, 2 will change, and it's a 1, 2 because we're looking at the correlation between variables y1 and y2. If we generically called them x and y, then we would say x and y under this correlation, just so we know what we're talking about. And it's the covariance divided by the product of the standard deviations. This is what normalizes it. Normalizes it means it, the maximum is 1 or minus 1. And that's one of the properties of correlation. Now, the closer that the correlation is to 1 or minus 1, the tighter the data point follow a straight line, or more, the strength of the linear relationship is more prominent. And so we can also show that if the absolute value of correlation is 1, so that means if correlation is 1 or minus 1, this implies a perfect linear relationship between y1 and y2 using this formula. And this is the formula of a line. Now, if it's 1, it's plus. If it's minus 1, it's minus here. But this is the formula. Now, the sample correlation is analogous to the population. So R12, which means we're taking the sample correlation between y1 and y2, and it's the sample covariance divided by the product of the standard deviations. Now, if we look at this, and this is, I'll, as always, post the R code in the comment section, but we're not going to review that because it just plots this data. So here it's the speed of a car and the stopping distance. Now this is data from 1920, so a little bit different in cars, but look at the regression line. The line sort of follows a tight relationship around that regression line. And so if we look at the correlation between speed and distance, it's 0.8, which is pretty strong for correlation. Now, we could also calculate it as the covariance between these variables divided by the product of the standard deviations, and we come up with the same thing. Or it's the covariance between the two variables divided by the square root of the product of the variances, and we get the same thing. But some, wonder why correlation is related to that linear line, and here's a sort of a quick illustration of why. So if we look at the simple linear regression line, it produces an intercept and a slope. So the slope of that regression line is 3.9. But if we take the correlation times the standard deviation of distance divided by the standard deviation of distance, it actually equals the slope of that line, right? So correlation is just it's a weighted slope. And that's why, that's one reason why it's a linear relationship, or describes that linear relationship. Now let's look at the population correlation matrix, which is denoted by capital P. And this tells us, so variable 1, row 1, variable 1, related to column 1, which is variable 1, is the correlation is 1. It's a perfect correlation with itself. That makes sense. The correlation between variable 1 and variable 2 goes here, which we denote row 1, 2. The correlation between variable 2 and row 1 is 2, 1. But it's the same two variables, so this is the same. And correlation matrices are symmetric, so the upper diagonal and lower diagonals are equal. Correlation between variable 2 and variable 2 is 1, so this is it. This is a correlation matrix. Now, since correlation is calculated from covariance, it seems like the correlation matrix should have a relationship with the covariance matrix, and it does. So if we create a diagonal matrix of the variances, and then we create a square root matrix, which is the diagonal of the square roots of these, which is the standard deviations, and then we look at the inverse of that square root matrix, but since it's diagonal, it's just 1 over the diagonal elements of this, right, which is this. And then it can easily be shown that the square root, the inverse of the square root matrix times the square root matrix is the identity matrix. So they are inverses of each other. And then this is the relationship. Capital P is the inverse of the square root matrix, sigma, which is the covariance matrix, times the inverse of the square root matrix, which are these, and then when you multiply these through, remember a diagonal times a matrix, this goes to each row, and this goes to each row. And then here, if you right multiply by a diagonal matrix, this goes to the columns, and that creates the correlations. Now the sample correlation matrix is analogous. It's capital R, and 1's down the diagonal, and then R, 1, 2 and R, 2, 2. Those are the same. It's symmetric. But this is the sample correlations between the variables. And that means there's a relationship between the sample covariance matrix S and the sample correlation matrix. So if we create diagonal elements analogous to before, we have a diagonal element of the sample variances, create a square root matrix from that, which means we take the square root of the diagonal elements, which is just the standard deviations of each variable, and then calculate an inverse of that square root matrix, which is this, and then it's easy to show that they are inverses of each other. Then the sample correlation matrix can be thought of as this matrix product multiplied out, and you get the sample correlation matrix. Now notice from the previous formula, we also get this one. So if we look at this relationship, R is equal to ds to the minus 1/2 s ds to the minus 1/2. If we left multiply by d to the 1/2 on both sides, and then we right multiply by d to the 1/2 to both sides, we get this relationship. So the covariance matrix is actually this matrix product using the correlation matrix. Now, a brief R illustration of this. If we store the car's data frame as a matrix, call it Y, then we store the covariance matrix of Y into capital S. And then we take the diagonal elements of S, which grabs the sample variances, but then we have to square root them, and then diag it, which creates that diagonal matrix. And if we look at the correlation of Y, the sample correlation, we get this matrix. 1's down the diagonal and 0.8068949 in the off diagonals. Notice it's symmetric. And then we take the inverse of this square root matrix times S times inverse of the square root matrix. Notice we get the same thing, same matrix. And as we should, Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.